So now we have some examples with a cubed root in the denominator. So now we're not looking for pairs, but rather groups of 3, so we can take the cubed root of it. So there's just one term in the denominator. Okay, so one radical term. Okay, but we'll talk more about that later. So right now on this first one, I have the cubed root of 7. So 7 is prime. I would need 2 more 7s to get a group of 3. So what I want to multiply, it has to be a cubed root, and I need 2 more 7s. Whatever I multiply in the numerator or denominator, I have to multiply in the numerator. So it looks like that. There's really a line under here, but sometimes that doesn't fit. Okay, so in the numerator, I get the cubed root of 49, which I can't take the cubed root of 49, so because there's just the 2 7s. Now what happened to that 1? It's just 1 times the cubed root of 49, so I don't need the 1. But now down in the denominator, I won't multiply it out, but you have the cubed root of 7 times 7 times 7. Well, that's enough. That's a group of 3, so it comes out. So I have the cubed root of 49. Don't forget to write the index. Over 7. I'm going to write it again because it's kind of messy. The cubed root of 49 over 7. And that's the answer. Again, you can't cancel the 7 into the 49 because the 7's not under the radical sign, but the 49 is. All right, so here's another one. We have the cubed root of 5 over 12. Now this one's a little bit trickier for me. I'm thinking, well, how could I get 12 to be, a perfect cube? But the thing is, I don't want to make it any bigger than I have to. So what I'm going to do, I'm going to keep it as a fraction under the cubed root for now. Keep it at 5 over. And I'm going to think of 12 in terms of its prime factors. 2 times 2 times 3. Okay, that's the prime factorization for 12. And now I can multiply by just what I need. I need groups of 3 because it's a cubed root. So I need another 2, and I need 2 more 3s. And then I'm going to multiply that in the numerator as well. So I get the cubed root. I guess I should make that a little longer. In the numerator, I have 5 times 2 times 3 times 3. I don't know what that is, but I'll figure it out in a minute. Now in the denominator, I've got the 3 2s, and then I've got 3 3s. So now I'm going to be able to take a 2 out, and I'm going to be able to take a 3 out. So I'm going to simplify this now as the cubed root of, okay, it's going to be 90, because it's 5 times 2 is 10, and then 3 times 3 is 9, so 9 times 10 is 90. Okay, then in the denominator, I have 1 2 and 1 3. So that's going to be the cubed root of 90 over 6. Now you might be asking, well, don't I want to try to break down the 90 and see if I can simplify that? I don't have to. I already know I can't because it already broke down into prime factors of 5, 2, 3, and 3, and there aren't any groups of 3. And so I'm done. That's the answer. All right, I think there's one more of these. Okay, so we have a cubed root in the denominator and just a 5 up there in the numerator. But again, I'm going to think of that 9 as 3 times 3 times y. And then I'm going to multiply by what I need to multiply by. So I'm going to need another 3. This is cubed root. Another 3. And then there's a y there, so I'm going to have 2 y's. Because I need everything to get to be groups of 3 so they can get out of the radical. I don't worry about what's going to happen in the numerator. I'm just trying to rationalize the denominator. Okay, so now that's going to give us, in the numerator, a 5. The 5 is just out there, times the cubed root of 3y squared over, and then I have the group of 3's, so I get 1 3 out, and I have a group of y's, and I get 1 y out. Now, if that 3 could go into 5, I would do something, but it can't, so I'm done. That is the answer. So it's easier to work with those prime factors. That'll save you a lot of heartache on these problems. Okay?